Okay, so we left off last class looking at a bunch of monoatomic ions. So these are ones that you can find on your periodic table. You have to have all of these memorized. But we talked about ways that you can have them memorized, right? So 1A, 2A, 3A are all just 1 plus 2 plus 3 plus. On the other side, counting backwards from A to A, our 7A, we've got 1 minus, our 6A, we've got 2 minus, our 5A, we've got 3 minus. And then we had that little staircase thing from aluminum, zinc to silver. So our plus 3, our plus 2, our plus 1, just the little staircase steps. And cadmium's also a 2 plus. We can use these to write formulas for ionic compounds. So ionic compounds are made of positively charged and negatively charged ions. So we've got positively and negatively charged ions. To start off writing the formulas, the chemical formulas using symbols, right, we've got to write the symbols for both of our ions, and we want to include the charges. So our positive ion, our negative ion. We are going to be doing relatively basic ionic compounds, so we'll have one positive ion, one negative ion. They can get a lot more complicated than that. So we're going to write out our symbols and the charges, and then we're going to take the magnitude, the number of the positive and the negative. We're going to swap them and make that the subscript of the other ion. We'll see examples of this. You can call this the crisscross method. You might also hear it called the swap and drop. If you're going to use this method, you also need to reduce the subscripts if possible, so that we've got basically an empirical formula. We want the ratio of the simplest whole number subscripts. And then we could also check to make sure that the sum of the charges of the cations, the positively charged ions, exactly cancels the sum of the charges of the anions, the negatively charged ions. So here's what that looks like. We want to write a formula for the compound that forms from aluminum and chlorine. So starting with aluminum and chlorine, we find aluminum on our periodic table. It's in group 3A. So aluminum is going to form a 3 plus charge. So Al 3 plus. This is part of why we memorize the charges. And then we've also got chlorine. Chlorine's in our 7A, so we can do the A designation group number minus 8, which would give us a 1 negative, or you can think of moving one spot over to get to our nucleic gases, so it's a 1 negative. Either way, you should come up with Cl minus. So that's our first step. We need to know what the charges are, and then we can crisscross. So we're going to take the charges, the number part, and make that the subscripts. So for aluminum, we had a 1 negative charge on chlorine, so we're just going to have a 1. The 3 plus, just the 3 comes along, so it's going to be Cl3. So Al, Cl, and a subscript of 3. If you're good at the mental math of figuring out how to get these numbers to pair up, what you need to multiply them by to get them all to cancel out, and you don't want to crisscross them, awesome. You don't have to crisscross them. You can just mental math your way through it if that's something that you can do and you feel comfortable doing. Okay, so we get AlCl3. Can we simplify or reduce those subscripts? No, we can't, right? Because we've got a 1 for aluminum, so it's already simplified. So nothing to do there. Already simplified, and if we wanted to, we could check the charges. Wait. So our aluminum, we've got 1 of them. It's a 3 plus charge. Our chlorine, we've got 3 of them with a 1 negative charge. So it's 3 negative, 3 positive, 3 negative. Those cancel out. And so this is a neutral formula, AlCl3. That would be our final formula for that compound. Questions on any of those steps? Cool. Now try writing a formula for the compound that forms from sodium and sulfur. All right, so the first thing that we want to do for making a compound that forms from sodium and sulfur is we need to figure out what's sodium, what's sulfur. So sodium has the symbol Na. Sulfur has the symbol S. And we can find those on our periodic table. Sodium is all the way on the far left, it's in our alkali metals group. It's our 1A column, so it's going to be sodium plus. Sulfur, we're going to find over here on our 6A. It's 2 spots over from the noble gases, so it's going to have a 2 negative charge, S2 minus. Hopefully, we can look at this and see, okay, we've got a 2 negative charge on the sulfur. Sodium has a 1 plus charge. What do we need to multiply 1 plus to get 2? 2. So we need 2 sodiums. So you can do it that way, or if you want to, you can just swap and drop or crisscross. That's always an option. And so this is going to turn into Na with a subscript of 2, and then S. And since we only have 1 sulfur, we can't simplify. And if we wanted to check our charges, we've got 2 sodiums, and they've got a 1 plus charge each. So we've got a total of 2 plus. We've got 1 sulfur that has a 2 negative charge, 2 plus, 2 negative. Those cancel out. We've got a neutral formula. So once you memorize the charges, or figure out how to get them from the periodic table, this becomes a relatively quick, hopefully painless process. So let's make it more complicated. So we also can write formulas that have polyatomic ions in them. And the tricky thing about polyatomic ions is that it's a lot of atoms together, and it's not always intuitive what the charge is going to be or what the name is going to be. So polyatomic ions, remember, the poly meaning many and atomic referring to atoms, means that we've got many atoms, and the ions part meaning that they have an overall charge. The names and the formulas for these are either going to be memorized, as is the case for some of these, or they're things that you can look up or deduce from other names and formulas. So a couple of the ones on here I believe that you have to have memorized: ammonium, acetate, chromate, dichromate. It's most of these. But this is not an exhaustive list of all the things. A lot of these ATE ending ions are ones that you'll want to have memorized. We'll learn some tools for coming up with some of the other naming conventions as well. And if you've got your green sheet, all of the polyatomic ions that you need to know show up on your green sheet as well, or you can come up with the name from the green sheet. Some that are not necessarily intuitive or things that you would come up with in this 8 ending are ammonium, acetate, dichromate, cyanide, hydroxide, and I think that's it for this list. So you need to know what's the name of the ion, the polyatomic ion group, what's the formula, and as part of the formula, what's the charge. The charge is very important. So for example, we want to write a formula for the compound that forms between calcium and nitrate ions. Calcium is Ca. We can find it on our periodic table in group 2A. It's an alkaline earth metal. Since it's in 2A and it's a metal, it's going to have a 2 plus charge. So Ca 2 plus. And then nitrate, this ATE ending clues us in that it's what we'll come to know as an oxyanion. It's a polyatomic ion. This is an ending that's reserved for polyatomic ions. So we would find on our green sheet on one of the sides, if you look up at the top, there's a bunch of oxyanions on the top there. And we'll find the one that's nitrate. And nitrate is NO3 minus from our periodic table. But then once we get here, the process is the same as with the ionic compounds we were doing before. It's just a crisscross or a swap and drop. So we've got 1 calcium ion, and this 2 goes to the NO3. So there's something extra that we need to add in. Who knows what that is? Parentheses, that's exactly right. Yeah, so we need parentheses so that we know that we've got 2 of the entire group. So the NO3 goes inside parentheses, and then the 2 goes on the outside. So this means we've got 2 of what's in the parentheses. you would not want to write out CaNO3 because that looks like we've got 32 oxygens. You also wouldn't want to multiply the 2 across the 3 and the 1 to get CaN2O6. You might see this occasionally, but that's not typically the way that we would write it because it's confusing for chemists. It's just not part of our typical rule set. So it would be this formula here. And we could also see if it's simplified. We can't simplify it anymore, so it's simplified because of the subscript of 1. And if we wanted to, we could check the charges, but they do work out. We could also write a formula for a compound that forms between aluminum and phosphate. So aluminum is Al. We find it on our periodic table in group 3A. So it has a charge of 3+. It's a metal. Metals get positive charges. And we've got the phosphate ion. Again, this ATE ending means we've got a polyatomic ion. So we would find something on our green sheet on the top. We would find phosphate. And it's PO4 with a 3 negative charge. Now we've got a choice. We can look and see that we've got a 3+ and a 3-, and those go together in a 1-to-1, and you can just combine them. So one option is just straight to AlPO4, and that works. That's great. Love it. Or we can crisscross. If we crisscross, we'll get Al3, open parentheses, PO4, close parentheses, 3. That's different than what we got just by combining them 1-to-1. What do we need to do? Can we simplify? We sure can simplify, and in this case we have to simplify. So we divide both of those subscripts by 3, and we would still end up with AlPO4. In this case, it's crucial that we do that simplification, otherwise it's wrong. So sometimes the crisscross method can get us into a little bit of trouble if we forget to reduce the subscripts. We won't have to do it a lot, but we will have to do it occasionally, and this is one of those instances. More fun with polyatomic ions. This one's for you to try. Write a formula for the compound that forms between potassium and sulfite ions. So this ITE ending is another of our polyatomic ion endings. I don't think you have this on your green sheet, so I'll just give it to you. Sulfite is SO3, 2-. So go ahead and come up with a formula for that compound. All right, so the place we want to start is getting our symbols and our charges. Potassium is K. We find potassium, guilty, no, on the first column are alkali metals, right? And so it's a 1A, so it's a 1+ charge. And sulfite, as I gave you here, is SO3, 2-. And we can crisscross them. That'll result in a 2 going over to the potassium. So we'll have K2, SO3. And we can't simplify because we only have one of our SO3 groups. So that would be a simplified and complete formula. Questions? If you're having trouble coming up or moving between the names and the symbols, I recommend you could probably find a tool online. There's also a quiz in the Exam 1 practice materials that you can do as many times as you want. So you could just, in your free time, like, hey, I've got a couple minutes, let me just check how well I know my elements and symbols, take a little 5-minute quiz. You don't have to think too hard about it. Just, all right, how'd I do? And then look through it. You can take that as many times as you want. Just do it every now and then, and before long, you'll be a pro. Okay, so now we're finally getting into nomenclature. So nomenclature is made up of these two parts. And if I'm remembering correctly, it's been a couple years since I looked it up. It basically breaks down into, I think it's crying list is one literal interpretation of it. Crying like the little boy on the corner, extra, extra, crying like yelling out reading. Really what it means is like it's a naming list, but crying list can feel really appropriate sometimes because the rules can feel a little bit obscure and a little too particular. They have to be particular, as we'll find out. So we're going to get into naming, and that's what we're going to be doing in lab. You'll be doing naming kind of throughout the entire rest of the class. So it's important that we learn our nomenclature and be able to move between names and formulas. The first part of naming anything is identifying what it is. If you were to go outside into the world without any knowledge of what any sort of animals are, and you went out and you saw somebody walking with a leash and an animal at the end of that leash, and you got home and you said, "Hey, Mom, I saw somebody was out in the neighborhood walking their chicken." Mom would probably go, "What do you mean walking their chicken? People don't walk their chickens." And you might have to describe what that chicken looked like, and it turns out that it was actually a cat or a dog. So that would be pretty confusing. Or if you said, "Hey, I saw a bunch of gophers flying around and landing in the trees and singing beautiful songs," people would be like, "What do you mean gophers? Gophers don't fly or sing songs. Maybe you saw birds?" So identifying the type of thing allows you to talk about it a little bit better, and for chemistry that's especially true. So a lot of compounds have a common name. So water, H2O, and ammonia, NH3, are two common chemicals where we'll typically use their common name, just what we normally call them, instead of their chemical, their systematic name. You should definitely know that water is H2O. It would also be a good idea to know that ammonia is NH3. Okay, so getting into our crying list, the first set of things we're going to talk about are ionic compounds. Ionic compounds is, I think, our biggest group. We're also going to learn some extra information as we're learning how to identify and name ionic compounds. So the first step in naming a thing, calling a thing a name, is identifying it. So identifying an ionic compound as an ionic compound. Anytime we have a metal and one or more nonmetals, we can assume that the compound is ionic. Compounds containing NH4+ are also ionic. So for example, NH4Cl. This is made up of a cation, NH4+, and an anion, Cl-. If you see a metal, it's an ionic compound. The metal will always come first. We can categorize them into two types, because one wasn't enough. We've got things where the cation can only have one possible charge, where it's always that charge. And this covers pretty much everything that we've talked about so far. So things like aluminum. Aluminum forms a 3+ charge. It's always going to be a 3+ charge. Our alkali metals, our first group, our 1As, those are all going to be a 1+ charge. Our group 2A, always going to be a 2+ charge. Zinc, always a 2+. Silver, always a 1+. So this includes all of those things. We've also got things that have more than one possible charge. For example, could be 2+, 3+, 4+, 5+, 6+, 7+. There are a couple of elements that have all of those options. And so we wouldn't know just by saying what the element is, which of those options or which of those charges it is. And so we'll learn how we specify that. So talking about the simpler one first, it's always that one charge. The name of the ion is the element name followed by ion. So for example, lithium, Li plus is the lithium ion. So just the name of the thing, add ion at the end. Al3 plus, aluminium ion. If we've got any Brits in the house, I don't think we do. Zinc and silver, zinc ion, silver ion. Not too bad, right? So we've got those. We've also got the metals that form more than one type of cation. So for those cations, this is typically our transition metals. So all the stuff in the middle except for zinc, silver, and cadmium. In this long rectangle in the middle from scandium all the way over to zinc, but not including scandium, zinc, silver, or cadmium, all of these have multiple charge options. And we are primarily going to be using the modern Stock nomenclature named after Alfred Stock. Thank you, Alfred Stock. Everyone say thank you, Alfred Stock. Thank you, Alfred Stock. Okay, nobody was on board with that. Here's why we're saying thank you, Alfred Stock. Thanks to Stock, the name of the ion is the element name followed by the charge in a Roman numeral in parentheses. This is easier than the old way. This is easier than the old way. So it might not feel great, it's easier. So our Roman numerals, in case we've forgotten, 7, 8, 9, 10. These, of course, are not the Roman numerals. The Roman numerals, we're using the letter I, we're using the letter B. We're probably not using the letter X, but I'm going to go to 10 anyway, just because. So 1, just one I. If 1's an I, then 2 I's, 2. And then we've got, I know you can't believe it, I. And then for 4, we use our symbol for 5, but we put 1 in front to let us know that we're subtracting. So this is 5 minus 1, which is 4. V is 5. And then if you put the smaller thing after, we're adding. So VI, VII. And we typically won't have to go to 8. You probably don't even need 9 or 10. However, knowing these symbols can be helpful for interpreting what Super Bowl it is, because Super Bowl also likes to use Roman numerals. But you'll also probably have to use some other Roman numerals in there. But this is helpful for understanding which Super Bowl we're talking about. Okay, so for all metals not in groups 1, 2, 3, A, zinc or silver or cadmium or scandium, for example, with iron, Fe2 plus, iron 2 ion. Fe3 plus, iron 3 ion. And then to be pedantic, there's no space between the end of the element name and the open parentheses, the front parentheses. There's no space there. If you put a space there, it doesn't really matter because you're not publishing scientific papers, but it's correct to not have a space there. Now here's why we said, or we're supposed to say, thank you, Alfred Stock. So we're looking at metals that form more than one type of cation, so same group of things. We've got our elements, just a couple of them over here on the left. We're going to look at some classical nomenclature. So elements over here on the left, and their stem. So this is like the base of the word, based on their old name, so where the symbol comes from. So iron has a symbol Fe, so it's Fer. Ferr is the start. And if you've got a 2 plus charge, the modern name, it's just iron 2 ion. Great, nice and easy. We know that it's a 2 plus ion. The old name, the classical nomenclature, that would be the ferrous ion. So Fe2 plus, ferrous ion. Fe3 plus, ferric ion. So we're using an older name version, and we're making the ending IC for the higher charged one, or OUS for the lower charged one. So OUS is lower charge, IC is the higher charge. And you might be thinking to yourself, that's not so bad. We just remember that 2 plus ends in OUS and 3 plus ends in IC. Not bad. No, wrong. Copper, the base name is Cooper, C-U-P-R, And it's got a 1 plus and a 2 plus. And the 1 plus is cuprous, and the 2 plus is cupric, which is not the same as with iron, where it was 2 plus and 3 plus. This is also different from tin, which is not just one charge difference, where it's tin 2 and tin 3. It's tin 2 and it's tin 4, and these are stannous and stannic. And that's also different from chromium, which is the same as iron. And then there's other charge variations as well. So this is why I was saying, we say thank you, Stock. Thank you for coming up with this easier nomenclature. If you take Chem 1, you will have to memorize the classical names as well. If you're going into a healthcare setting, I would recommend memorizing the iron 2 and the iron 3. I might make it required, because apparently those show up if you're going into an allied health field. Questions about these? So again, we get to learn the modern name, the stock nomenclature, the easier one, with the Roman numerals. So you have to learn your Roman numerals if you don't remember them, but you don't have to remember all of this other stuff like plumbus and plumbic and what those mean, which is cool. Okay, so that was all of our cations, positively charged things. So those are what show up first in our formula. On monoatomic ions, so negatively charged ions. If it's monoatomic, mono meaning one atom ions, so it's just one type of element, then we change the ending of the name to IDE and also add ion at the end. Usually you can just change the ending to IDE, and any chemist will know, oh, you're talking about the ion because you used the ending of the name that signifies that it's an ion. So it's all it's like learning a new language is really what it is. So that IDE ending means it's an ion, and it means that it's just that one thing, it's monoatomic. So for example, F minus, F is fluorine. The U comes before the O. It's not fluorine, it's fluorine. And fluor, F-L-U-O-R, is the base. And so if we make it F minus, we change the ending to ide. And so it becomes fluoride, the ion that's added to most residential drinking water supplies and also shows up in lots of toothpastes. Can do the same thing for the rest of our halogens. We can do them for our 2 negative charge things as well. So oxygen, the base is just ox. You change the ending to ide and add ion. So oxide ion. I think these are relatively simple. Just change the ending to ide. You kind of have to remember what the base is. If you get it wrong, as long as it's like recognizable, it shouldn't be too much of an issue. Okay, so naming ionic compounds. When we are naming ionic compounds in this class, there are always going to be only 2 ions. We'll have our cation, which is positive, and our anion, which is negative. The name of the ionic compound is cation name plus anion name. It's as simple as smush them together. You just take off the ion part. The cation is going to be the first element. Ammonium might sometimes show up at the end. It just kind of depends on who is writing it. And then the anion is going to be everything else. So if you've got a metal or something, that'll always show up in the front, and then the negatively charged anion will show up at the back. So some examples. We've got CaCl2. What is the name of Ca? Ca is calcium, lowercase c, A-L-C-I-U-M. What charge does calcium form when it's an ion? It's a 2 plus. It's in the 2A. It's a 2 plus. Is it always a 2 plus? Yeah, it's always a 2 plus because we knew that it was a 2 plus. So it's just calcium. You don't have to specify what charge it is. And we would add ion if we were just talking about the calcium. And then Cl is what? Cl is chlorine, but we've got the ion version. So it's chloride. So calcium chloride, the whole name. We don't have to specify that there's 2 chlorines or that there's 2 chloride ions. We would figure that out based on their charges. Name the compound AlF3. What is Al? Al is aluminum. Aluminum's one of our cations. It's always the same charge. It's always a 3+, so we don't have to specify. We just write aluminum. And then F is fluorine. We've got the ion version, so instead of ending in -ene, it ends in -ide. So aluminum fluoride. That's it. That's the whole name. We've also got KCl. K is potassium. We just write the name because it's K+. It's always going to be a 1+ charge because it's an alkali metal. It's a main group. So it's always going to be the same charge. And then Cl is chlorine. We've got the ion version, and so we change the ending to IDE. So it's potassium chloride. That's the whole name. That's not too bad. Nothing to cry about. We're just getting started. Any questions so far? These ones, relatively easy. It's always the same charge. You just put the names together. Just put the ion names together, change the ending to "ide" for the monoatomic ion. If we wanted to go backwards, or if we were going from a name, if we wanted to determine the charge on the cation for whatever reason, if we need to, if the metal forms more than one type of ion, then the charge is determined from the chemical formula. So we'll be going mostly from formula to name. The first thing we want to do is determine the charge on the anion. So we want to figure out how much negative charge do we have. We know that the sum of all the charges must be 0. What this means is positive charge equals or cancels the negative charge. So if we figure out how much negative charge we have from our anion, we can figure out how much total positive charge we have. We can figure out how much positive charge each of our cations has. So for example, in Fe2O3, Fe is one of our transition metals. It's iron. We don't know what the charge is going to be. It's got a couple of different options. It could be ferrous, it could be ferric, it could be some other 3rd, 4th, 5th, 6th thing. Oxygen, however, is in a main group. It's one of our main group elements. So it's always going to form the same charge. What charge does oxygen form as an ion? -2. It's going to be O2 minus. So it's got a 2 negative charge, and how many of those do we have? How many oxygens? 3 oxygens, right? So we've got a total of a 6 negative charge. And our iron, whatever it is, has to equal a 6 positive charge. So in total, our 2 irons have to have a total of a 6 positive charge to balance out the 6 negative charge. And we've got how many irons? 2. So 2 times what gives us 6? X is 3+. So this would be, can't cancel out an X. X would be 3+. So this is iron 3. So a little bit of algebra. Any questions about how I did any of that? If you're confused or contused, now would be a great time to ask, or when we're working on the nomenclature worksheet. All right, some more similar ones to try. Name the compound PbO. Pb is lead. Lead is in the main group. However, it's in this mysterious 4A column. So lead, as it turns out, can have multiple charge options. We also saw it on our nomenclature table, plumbus or plumbic. So lead has a couple of options for its charge, so we're not sure what it is. However, oxygen always forms the same charge, which is O2 minus. To balance out 2 minus and a total of 2 minus, what do we need on our lead? 2, but positive. So it's Pb 2 plus. Since we only have one lead, the 2 plus balances out the 2 negative. So we've got the charge on our lead. We need the charge so that we can name it. So it's lead. How do we specify that it's a 2 positive charge? Who remembers that fun feature? 2 and 4 are the classical naming options. That's true. But how do we write it out with the stock nomenclature? Who remembers? Anyone? Parentheses, and 2 in Roman numerals is just II. So that's lead. And then we've got oxygen, and we change the ending to IDE. So this is lead 2 oxide. The 2 is to let us know that the lead has a 2 plus charge. If we didn't specify, it could also be, just to show you what it could be, if we just wrote lead oxide, it could also be a 4 positive charge, and that would be PbO2. So this is to allow us to distinguish between PbO2 and PbO. That's why we have to specify the charge. There's probably also some variant where you could make a lead 3 oxide, and that would be even worse. Okay, go ahead and try naming the compound Cu2S. Okay, so coming back to the name for Cu2S, we've got copper. Cu is copper, right? So another way that we could do these is we could just write out the name to start and figure out what we need to fill in. So we know, because it's copper and sulfur, this is going to be some form of copper sulfide. The UR ending turns into an IDE. What charge does copper have? Just generally. Generally, we're not sure, right? It's one of our transition metal elements, so we need to leave some parentheses. We're going to have to figure out what the charge on copper is. But we could start off writing this copper parentheses spot sulfide and then figure out what goes in the parentheses. Our sulfur, if we find sulfur, it's a 6A. It needs to move over 2 spots to get to the noble gases, so it's a 2 negative charge. Or we could do, since it's in 6A, we could do 6 minus 8, negative 2. It's got a 2 minus charge. We've just got one of them, so it's an overall 2 negative charge. We've got 2 coppers that have to balance out that charge. So in total, the coppers have to have a 2 plus charge. So whatever the charge is on copper times 2 needs to equal 2 plus. So the charge on the copper has to be 1. So this would be copper 1 sulfide. Not too bad? All right, we also have not just monoatomic ions, we have oxyanions. Most of our polyatomic ions are going to be oxyanions. The oxy part meaning oxygen. Just like OxyClean uses the power of oxygen. Same idea. So these are anions that contain oxygen. The unfortunate thing about this is that there's some memorization to do. The fortunate thing about this is that it's systematic, and so there's not as much memorization to do as it might look like initially. They're named systematically. The one that you should memorize is the one that ends in ATE. On your green sheet, on the side that's got all the ions on it, if you look at the top, there's a whole table of all of the different oxyanions and the ATE forms. They're listed out in the way that their non-oxygen, non-metal shows up. So carbonate, nitrate are next to each other. If you move one down from nitrate, phosphate, over sulfate, chlorate, etc., it's laid out in the same way that they're laid out on the periodic table. You need to know how many oxygens and what the charge is. From that ATE ending, if you take off one oxygen, it changes the ending to ITE in the same way that things that are marketed as light have fewer calories generally. So nitrate is NO3 minus. If you take off one oxygen, now it's NO2. It's got the light ending, the ITE ending, so it's nitrite. So 8 turns into ite. The only thing that changes is the number of oxygens. Notice that the charge is the same. So in a series of oxyanions, the charge always stays the same. So that's kind of nice. Looking at another example, sulfate. This is the one that you would memorize, SO42 minus. If we lose one of our oxygens, it goes from SO42 minus to SO32 minus, and so the ending changes to ITE. This is the -1 oxygen form. And again, the charge doesn't change. It's the same charge for the entire series. We can also add prefixes on. So we've got a couple of other options. If there's more than 2 ions in a series for these oxyanions, we've got the prefix hypo, which means less than. Like in the word hypoallergenic, things that give you less of an allergic response. Great if you're allergic to that particular thing. Hypoallergenic cats or dogs or perfumes. Or hypodermic needles. There's also a per prefix, meaning more than, like in hyper. If you're hyperactive, you're not just active, you're extra active. And so per does the same thing for us. In each of these, so the per means add one. The hypo means take one away. And we'll add these on top of our endings. So the base ending that we would memorize, the ATE ending. If you add 1 to the ATE ending, that's when we add in the per prefix. So from chlorate, instead of ClO3 minus, it becomes ClO4 minus. We add the per prefix in front. Just like on the previous slide, we can remove one oxygen. That changes the ATE to ITE. That's our first oxygen that we take off. If we take off another, that's when we throw in the hypo prefix. So subtracting 2 oxygens, we need both the ITE ending and the hypo prefix. And for all of these, the charge doesn't change. It's just the number of oxygens that changes. You've also got these rules on your green sheet. It's the second table, I think. It shows you what happens if you add 1, what happens if you subtract 1 or 2 oxygens. So some examples of working with these. So this is our most complicated form, I think, of ionic compounds. So we've got an oxyanion. CO2, we need to know what is CO2. What is this oxyanion? The reason we need to know what that oxyanion is because we've got Cr. Cr is chromium, which is one of our transition metals. Since it's a transition metal, we don't know what the charge is. So we have to figure that out from the oxyanion. So we would think about what starts with carbon and has oxygen. What's our oxyanion? Or we would look at our green sheet up at the top. We'd find the carbon one. What do we find for the carbon one? What looks like CO2 that's on our oxyanion sheet? Looks like carbonate. And I'm going to move that. So this looks like carbonate, which is CO3 2 minus. We've got CO2. It would still be 2 minus because we never changed the charge. So how have we changed from CO3 2 minus to CO2 2 minus? What's different about those formulas? We changed the number of oxygens, right? We have one fewer oxygen. So going from the 8 form, if we remove one oxygen, what does that change to? Ite. So this is carbonite, like what Han Solo is encased in. So carbonite, we've got CO2 2 minus. So great, we've got the ending, carbonite, and we know that the Cr is chromium, so we could write that in as well. But we do not know the charge of the chromium, so we'll leave some space for that. So looking at our formula, we've got Cr, CO2, 2. The chromium is the positively charged part. The carbonite is the negatively charged part. This has a 2 negative charge, and we've got 2 of them. So 2 times a 2 negative charge. We've got a total for our negatives of 4 minus. So that means to balance out 4 minus, we have to have 4 plus. Since we just have one chromium, that means our chromium has to be a 4 plus. So this is chromium 4 carbonite. And then we also have CONO3. What is CO? CO is cobalt. Cobalt is also a transition metal, and it's not zinc, cadmium, or silver, so we don't know what the charge is. So we'll leave a space. We've got to figure out what the cobalt's charge is. So we'll look at our anion, NO3. NO3 is an oxyanion. Which oxyanion does it look like? What do we have that has nitrogen in it on our green sheet? We've got nitrate, and nitrate is what? NO3, and what's the charge? Negative. That's what we have, right? We have NO3. So it's cobalt something nitrate. Doing our charge breakdown, our nitrate is 1 minus. We've only got one of them. So what does our cobalt have to balance out 1 minus? What's the opposite of 1 minus? 1 positive. So it's cobalt 1 plus, so cobalt 1 nitrate. So a little bit of algebra. It's not complicated algebra, just a little bit of algebra. Questions? All right. I also want to talk about molecular compounds because I think it's easy. It's easier than ionic compounds in my opinion. So I don't feel bad about making our Wednesday lab people just watch this in a video. So the first step, just like with ionic compounds, the first step in naming a molecular compound is identifying it as one. Molecular compounds contain 2 or more nonmetals. We are going to be learning the simplest form of molecular compounds, binary. Binary means two things. In this case, the 2 things we're talking about are 2 elements. So we're going to learn 2-element molecular compounds. For naming molecular compounds, there is some memorization still. We've got prefixes. So prefixes are used to indicate how many of each of the atoms we have. Lots of these are ones that you hopefully know. So mono, 1, di, 2, tri, 3. Tetra is 4. Penta is 5, like pentagon. Hexa has an X in it, so it's 6. Then we've got one of the weird ones, hepta. We've got octa, like an octopus. Octopuses have 8 arms. And then we've got nona, which is 9. Another weird one. And by weird, I just mean this is one that you probably haven't seen before. And then deca for 10, like in decade, which is 10 years. So for a lot of us, probably the only ones that we'd have to memorize are hepta, which does come up fairly often, and nona, which doesn't come up quite as often. It kind of looks like 9. If you just change some of the vowels, it's 9. Questions about any of those prefixes? Cool. All right, so for naming molecular compounds, the one weird trick is if there's only one of the first ion or first element, we omit the mono. So omit mono for the first element, only if it's mono. If it's anything else, we include it. This is just another one of those chemists saving time by doing the absolute least. So for example, CO2, we've got carbon first, so mono, then the name of the thing, but we omit the mono, so no mono. Carbon. Then we've got oxygen. We've got 2 of them, so we use the prefix for 2. Di. The base for oxygen, and then change the ending to IDE. So that IDE is standard, normal. So our full name for this is carbon dioxide, CO2. There's another weird trick. This one's less important. When the prefix ends in a vowel and the base name starts with a vowel, the first vowel is sometimes dropped. This one, if you don't do it, it's really not that big of a deal. So here's an example of that. So N2O, we've got 2 of our first thing, so di, and then the name of what it is, so dinitrogen, 2 nitrogens. We've got 1 oxygen. So we do the mono prefix. Oxygen already starts with an O, and so we get rid of one of them when we turn it into the ide. So it turns into monoxide. Other examples would be like if you had 5. This would be pentaoxide. And if you wrote pentaoxide, anyone would understand what you mean. But by convention, we would typically pronounce and probably write this as well, just as pentoxide. Again, chemists just doing the absolute least whenever possible. And that's it. That's all for naming for molecular compounds. So some examples, N2O4. What's our first element? Nitrogen. How many nitrogens do we have? We've got 2. What's our prefix for 2? Di. So dinitrogen. Our prefix for 4 for our oxygens is what? Tetra, like the fish. The base for oxygen is ox. And we change the ending to IDE. Notice we've got 2 vowels in a row. So we're typically going to drop this A, or at least when we pronounce it, we drop the A. So this would be dinitrogen tetroxide. Again, not really important that you drop that A, just that's a convention thing. That's the sort of like minor detail thing that if you looked it up, Google would just change it for you. Or if you were talking to a chemist, they would just say, oh, did you mean this other thing? Or they would just like, oh, okay, yeah, I know what you're talking about, because I'm not a pedantic word that I'm not going to say. All right, we want to name the compound NH3. It has a common name, ammonia. We're not going to use the common name. We're going to figure out what's the IUPAC, or what's the nomenclature name. What's our first thing? First element. Nitrogen. How many nitrogens do we have? 1. Our prefix 1. Mono. However, it's our first thing, and so we omit the mono. So no mono, just nitrogen. And then we've got, what's our next thing? Hydrogen. Base for hydrogen is hydr. How many of them do we have? How many hydrogens do we have? 3. What's our prefix for 3? Tri, like triforce. And we change the ending to IDE. So our full name, nitrogen trihydride. But we would typically just call this ammonia. Okay, we'll stop there. Any questions before we wrap? Perfect.